Hello everyone, my name is Li Xin and I'm a master student in Peking University. I am glad to introduce our work, Level Margin Planar Regularities for Point, Line, Visual-Inertial Odometry. Let me introduce our motivation first. In recent years, some researchers using Visual-Inertial Odometry generate 3D mesh map online. A 3D mesh map allows for extracting the structure of skin, which can potentially be used to improve simultaneously the accuracy of pose estimates and the mesh itself. However, their mesh map does not fit the environment well, since their mesh map are generated based on structureless sparse points. Therefore, we add line features with structural information when generating mesh map, which can make our 3D mesh map more in line with real space. There are our main contributions. Firstly, we propose a non-iteratively plane detect method with a 3D mesh generation method based on sparse points and a spatial line for monocular VIO. Thirdly, we developed a Thailand-coupled monocular Visual-Inertial Odometry system that utilizes heterogeneous visual features, include points, line, and plane, as well as their co-planar constraints. Thirdly, we provide Bayesian experiments to verify the effectiveness of heterogeneous features on both synthetic data and Oracle datasets. Let me introduce our 3D mesh map generation method. Since it is difficult to directly generate 3D mesh map from sparse 3D landmarks, we build 3D mesh from 2D mesh, both points and line features. Firstly, we detect points and line features in the last keyframe. Then, we use constraints de-Lorentz triangulation algorithm to build a 2D mesh from these points and line segments. Finally, we get the 3D mesh by projecting the 2D mesh into 3D space. After we get in 3D mesh in the skin, we can detect the plane from these triangulation patches and spatial line, utilize both triangulation patches and all spatial line to detect the plane is more suitable for not only point-rich but also textureless skin, compared to utilizing only triangular patches or only lines. This is overview of our proposed PLP-VIO system. The system is derived from our previous work, PL-VIO, which incorporate with line features into Wings model. The front-end model is used to extract information from the raw measures, and the 3D points, lines, mesh map, and the body states are estimated with sliding window optimization in the backend. We build our VIO system with the sliding window optimization, which estimate body states and 3D landmarks by fusing MU and visual informations. The 4-state vector of our VIO system within a sliding window contains the MU states, point features, dips, 3D line landmarks, and plane states. We optimize all the states variables in the sliding window by minimizing the sum of cost term from all the measurement residues. These two terms of the first rule are period residue and MU measure residues. The second rule is projection residue of point and line features. The last rule contains point on plane residue and line on plane residues. For point feature measurement model, the reprojection error of a 3D point is the distance between the project point and the observed point in the normalized image plane. The reprojection error is defined as follows. The setting of covariance matrix is based on assumption that the future point coordinates are affected by exotic white Gaussian noise. The standard deviation of the noise is set with 1 pixel. For line features measurement model, the reprojection error usually defined as the distance from the endpoints of line segments to the projection line in the normalized image plane. In our system, we normalize the distance with line segment lines because of the observation of the same spatial line in different forms have different lengths. If you are interested in 3D line translation in the different coordinates and how to compute the residue and Jacobians, we recommend you to read PLP-VIO. The setting of covariance matrix of line features residue is same as the point features. We assumed that the endpoints of the line segments is also affected by white Gaussian noise as with point features. For plane feature measurement model, 3D landmarks co-plane constraints are defined by distance from 3D landmarks to the 3D plane. The point on plane residue is the distance of the 3D point to plane. Line features are a little more complicated than points. A line on plane can provide information from two aspects. First, every point on the spatial line must be on the plane. Second, the direction of this line and the plane normal vector are orthogonal. So the residue of line-on-plane constraints contains two terms. We model the distance residue with Gaussian noise with the standard deviation with 1 cm. As for the angle uncertainty, the deviation device is setting with 1 degree. This is the demo of our PLP-VIO. To evaluate our proposed approach, we conduct experiments on synchronic data and Oracle datasets. As shown in the picture, the trajectory of our PLP-VIO is more accuracy and robust than with mono. We evaluate the RMSE APE of pipeline OK-Wings, P, PP, PL, and PLP on Oracle datasets. We denote with mono as P, which only use point features. The PP use point features and co-planarity constraints. The PL-VIO as PL, which use both point and line features. And our method is denoted as PLP, which use point, line, and co-planarity constraints. We choose absolutely post error as the main evaluation metric. We can observe that our PLP method performs best in almost all sequences. Since our art, planar regularities and line features structural information in our PLP system, the merge map generated by our PLP method is more accuracy and more complete than P method. The video shows the 3D merge map of sequence V101 of Oracle datasets. The mean distance error of our PLP method is 2.8 cm. It's lower than the P method result, 3.6 cm. We also evaluate the runtime of different approaches. Thank you for your attention to our work.